And I would like to invite Vivek Sarkar, Professor Sarkar from Rice University, to introduce the next speaker.
Thank you, Mark. On behalf of the Ken Kennedy Award Committee, it is my real pleasure to introduce this year's winner, Bill Gropp. But I realize that Bill needs no introduction to the SC community. So I'm going to just spend a minute or two talking about the award itself. The Ken Kennedy Award recognizes outstanding contributions to programmability or productivity in high-performance computing with significant community service or mentoring contributions. The award, of course, is in memory of Ken Kennedy, who exemplified these qualities and was a dear friend to many of us. And the award committee was absolutely delighted to see Bill Gropp's nomination because he exemplifies these contributions through MPI, PET-C, and the truly amazing service he's done to the supercomputing community. So with that, please join me in welcoming Bill Gropp.
Well, thank you. And this is really an amazing honor. I knew Ken. I learned a lot from Ken. And I really do want to focus in this talk on the part that I think is really the most important, which is mentoring and serving the community as we go forward, because we face a lot of hard problems. Now, the thing I want to start with, I realized I needed a good Ken story. And Ken is really well known for his contributions, particularly for parallel compilers and languages, improving the productivity of parallel computing. But many of you may not know that without Ken, I don't think MPI would have ever happened. He called a workshop on standardization of message passing in Williamsburg in the summer of 1992. And he was interested in discovering whether there was some way for him to concentrate on building a better, more productive environment by having a lower level that was standard, so that as they wrote code, they didn't have to deal with each vendor's idiosyncrasies, not just in the semantics of how you express message passing, but or the syntax, but the semantics of what it means, what exactly happens. And at the end of this, we were pretty sure we knew the answer. And the answer to this question was clearly no. There were too many differences. There were too many things that we looked at differently in these systems. And Ken stood up and told us, this is great. We can do this. We should all get together, or you guys should get together, because I'm not a message passing person, and work it out. And of course, he was right. And the result has been a system that has allowed science to progress over the last more than 2 decades. And so one of the lessons there is really find solutions that work, independent of what you think. So Ken was committed to a more productive, what he viewed as a more productive model. I think when it works, it is a more productive model. But he realized that you needed a way to deal with another part of the productivity issue, the productivity in the portability, and that portability had to include performance. And so one of the things I want to say a little bit about is how we train our students to think precisely and quantitatively about parallel computing. This is because parallel computing is hard. No one who doesn't do it for fun, which may be a lot of this audience, but the rest of the people who are confronted with parallel computing would be much happier if they just had a single core that ran fast enough to do their work. And in many cases, they now have that. But if they don't, they have to use parallelism. And parallelism is, in fact, hard. But we need to be more scientific about evaluating the different approaches and understanding what works in the directions in which we need to go. And we need to set that example for our students. We need to hold ourselves to that standard. I'm going to show some examples of what I will call fuzzy thinking, so you can sort of think of this as me being a little bit of a curmudgeon here, but I will end on an upbeat note. But I do think we need to insist that our students be more rigorous and follow the scientific method. Okay, so we need to separate opinion from fact. And so here's some very nice examples. There was a big study looking at how we would get to a petaflop. This was a tremendous amount of foresight because we hadn't yet gotten to a teraflop. And we find quotes like this. So here, the software for the current generation of 100 gigaflop machines is not adequate to be scaled to a teraflop. And people firmly believe that. There's only one problem with that statement. The software that they're talking about is what we're running on 100 petaflop systems today. And in fact, it's likely to be, almost certainly will be, the software that will be running at exaflop. Now, maybe we could have done something different, but it wasn't the case that that software was inadequate. It was the case that that software wasn't as beautiful or as easy to use as we would have liked. Those are very different statements. And we can do better. So there's another quote in here. It says that petaflop's computer is achievable at reasonable cost with the technology available in about 20 years. So this was, again, 1995. And as part of that prediction, there was an estimated clock speed for systems in 2004 of 700 megahertz. And you might think, well, oh, they really missed it. Processors were much faster then. But in fact, if you looked at where the sweet point was in the clock speed of a processor, in terms of where would you operate it if you weren't trying to satisfy the marketing people by making your clock speed faster than somebody else's, that was a sweet spot. And the proof is that that was exactly the speed of the processors in the BGL. And so the people who had approached this problem quantitatively, what do we know? Do an extrapolation. Of course, extrapolation is dangerous, but work with the numbers that we have to understand where we're going. They nailed it. The people who looked at the software and thought about it very qualitatively, ooh, this is too ugly, completely missed it. Okay. So a few examples of fuzzy thinking that I think we all see all too often. Here's an example of two scalability curves. So I might have get a paper to look at that shows that I've got this great new algorithm. It's really scalable. And I compare it to this other algorithm, which clearly is not scalable. Which of those should I use? So think of yourself as asking this as a qual question to a student. Okay, what answer would you like to hear from them? Well, here's the same graph, except now instead of doing scalability, I've done time. And so algorithm one is, in fact, much more scalable. It's just a billion times slower than the other one. And that other one is, in fact, not scalable. It really falls off there after about 10,000 processors, but it's still faster. It's really the time to solution that's important. There is information content in whether something is scalable, but it has to be taken in context. You have to understand how fast the base is. You know, am I scaling from a terrible position, or I'm scaling from a very fast position? And there are two ways to improve your scalability, and I think we've all seen examples of both of this. One of the easiest one is to simply make sure that the per-core performance is terrible. And that's pretty easy because you can, for example, neglect to vectorize your code, because that's another part of parallel programming that's surprisingly hard. Or you can use a much more computationally intensive algorithm that gives you a lot more work to do, maybe more work than another approach, which makes it more challenging to scale. So how should you be thinking about speed up? Well, you need to put it in context. You need to understand the algorithm and its options. And some of these are not obvious. So for example, in-body force calculations can be done in O of n time for in-bodies. You know, better than n log n, certainly much better than n squared. One that I find that students often are unaware of is a broadcast of n words can be done in order n time, even better than order n log p. There's a clever way to shuffle and recombine that eliminates the log p term. You can also do things to evaluate implementation quality. and here I have a nice connection to Bill Camp's work, is that we were looking at a computation of exterior computational fluid dynamics on an unstructured mesh, very challenging problem even today. And we were doing well enough that we were excited about the opportunity to try to win one of the Gordon Bell Prizes. But to do that, we faced a real challenge because it's a sparse matrix calculation, it's memory reference bound. We were never going to get this kind of peak floating point rates that you would get with dense matrix operations. We were able to convince the committee by doing a performance analysis, looking at what was achievable on the system to show that our per core performance was close to what you could possibly get on the system. And by that, we could then make a convincing case that our speed up numbers were meaningful because the base performance was now good, and by using an unstructured grid and good sparse matrix algorithms, Krylov methods for solving the system of linear equations, we were using good algorithms. And I will say the connection, our result, which won us a Gordon Bell Prize in the special category in '99, was done on the Sandia T-flops machine. So an excellent system that allowed us to demonstrate another way of thinking about your scalability and your performance. So another example of fuzzy thinking that I see all too often seems to come from this very simple question: how do I compare two programming models? First, when you ask that question, that probably is what you want to know. Although in some cases, particularly if you're a developer, you want to know the answer to a different question. But part of that, first of all, is are you comparing a programming model? So, okay, or a programming system. So, well, what's the difference? Well, message passing is a programming model. MPI is a programming system that implements message passing, but also implements some other programming models. And this is true for most systems that we use. They implement more than just a pure instance of a theoretical programming model. But in fact, when people say they are comparing programming models, they're almost always comparing implementations of programming systems. Okay, so almost always those implementations. Well, one implication of this, and I hope you will all join me in taking a vow to do this, is that any time you get a paper that says, I'm comparing X to Y, where that's a programming model, when in fact, it's comparing the implementation of a programming system on some hardware to an implementation of a different programming system, I hope on the same hardware, but even there, sometimes it's different hardware, that you insist that that might be interesting data, but it's not comparing the programming models. It's comparing those implementations. And this is also important, and here again, for the faculty members who are looking for qual questions, here's another one you can use. What conclusions can you draw from this comparison? So I'm drawing this from a vendor that will remain nameless, that showed that their system that you could use instead of MPI was 3 times faster for long messages. Right? That was what you were supposed to draw from this. But there's, in fact, a very different message one should draw from this. So think about this. They've got a fast way to move data from one place to another. I can certainly implement MPI using that. What this told me was that they had no clue what they were doing. And is that the message that they wanted to promote? Right? So it's very important to think very precisely about what it is you're saying, what it is you're showing there. Here's another example that I use, and I, in fact, have been somewhat sloppy in taking advantage of this. Now, this is, I love this result because I had nothing to do with it. It's a comparison of some graph frameworks, and I've taken this directly from the paper. And so there's this beautiful result here. You can see there's this factor of 100 from some very popular graph frameworks compared to something that they called native. Now, their idea of native was we will write this particular problem at a low-level system and then compare how fast these frameworks get to that system. So in some sense, they are comparing those implementations. Well, what I like to usually point out is that if you read far enough into the paper, you discover that native is MPI, right? So MPI, yay, yay, yay. But in fact, what I should be saying is that that's some MPI implementation. Right? It's not really a comparison with MPI, it's a comparison with some implementation. Another one that we all tend to be sloppy about, I'm as guilty of this, I think, as many of us, is being careful about how we describe our experiments to make them reproducible. And this is becoming increasingly important as science and the society has become increasingly aware of just how irreproducible some of our results have been. And there are certainly lots of challenges here, but there are things that we can do to improve the situation. Simple ones are just describing more precisely what our experiment is. What is the apparatus? So for us, what's the system? What's the compiler version and options? What does the source code look like? What's the input data? One easy one, how many of us have even been guilty of taking the data that's been printed out, for example, time measurements, and picking it up and plopping it into our paper, right? How many of those digits could you reproduce? How many of them are even significant? Right? That's sloppy. It draws attention away from what's real. Without looking at how accurate those numbers are, how do you interpret it? We should all be better about this. Another example is how do we describe things? We tend to be a little fuzzy about the names that we use. If you look at journal articles in other disciplines, many of them will start with a block of text that explains the nomenclature, just so that everyone is precise about it. And so I paraphrased something that I'm sure many of us have heard, is that, so programming exascale systems, that will require moving beyond the bulk singularist programming model, and we will need to replace MPI with, and then there's usually something that's being offered up as the replacement. So what's wrong with this statement? There's actually a number of things wrong with it. First of all, there's this statement given as fact that exascale systems require moving beyond BSP. Now, I personally may believe it, but it's a hypothesis. It is not a fact. How would you test or demonstrate it? Right? Again, I believe this is probably true, but that's different than saying it is true. But there's a more subtle error in here, which is there's the implication by the way it's worded that MPI is a BSP system, that you need a completely different infrastructure on which to implement a non-BSP style programming system. And that's completely false. It's worded that way to sort of to encourage you to move past MPI. That's at best misleading, it's somewhat disingenuous. I could use firmer terms for that. I would with a student. It's true that MPI makes it easy to emulate a BSP system, but it's also true that even MPI 1 contained everything that you needed to build a more adaptive system. Now, we can talk about whether it has everything you need to build it as efficiently as possible, but that's a different question. The other thing that's missed in here, particularly it's sort of amusing, often getting this from people who think that the system should be more productive, is there's a reason why there's so much BSP code out there. It's because programmers like it. It's easy to reason about. It's easy to think about. BSP, in many ways, is beautiful because it includes something that you really should have for a parallel programming model, which is a performance model with it. The only reason you're doing parallel programming is to achieve performance. So your performance model should be part of your programming model. So these are all things to be thinking about and thinking precisely about, thinking about them with rigor rather than being fuzzy about it as you're trying to get to where you personally want to go. And the last example I'm going to give is going to make sure that we understand what it is we're asking for, because you can ask the wrong question and then cause real harm to the community. And it's one of those things. It's easier for me to say this now since I'm an acting director of an HPC center, so I'm part of the guilty parties here. But I/O performance for applications, even science applications, certainly this is even more important as you're looking at big data applications, is appallingly poor. And I will show you just how appallingly poor in a few slides. And we really need to solve this problem, and we're not going to solve it by saying the vendors just have to get off their tails and make things faster. This is not the way it will get fixed. And the community and the HPC centers, I believe, has really been complicit in this because we've been asking for the wrong thing. Okay? So what is the question that causes so much trouble? We ask the applications people if they need POSIX I/O. Why is that the problem? Well, first, let's see how bad it is. So here's an example drawn from 4 different supercomputers, and it's the percentage of applications that achieve a certain sustained I/O throughput. In some cases, if the amount of data that's being moved is fairly short, they'll exceed the sustained bandwidth because it gets cached at the server side. So that's why some things go above the top lines. Well, what you see is that there are few applications that do well, but by the time you're down at 25%, you're as much as 3 orders of magnitude below the sustained performance. And it continues to drop. And this is terrible. Right? I can build a much cheaper I/O system if I only need to make it 1/1000th as capable. So I could use 2 disks instead of 20,000. Okay. So what are some of the problems? POSIX I/O has very strong consistency model, which makes it extremely hard to cache effectively. Applications have to do lots of things to keep POSIX happy. It also adds a lot of fragility to the system. So the single biggest source of failures on most large HPC systems is the file system. Okay. The files as I/O objects also add lots of metadata choke points. These impact performance in ways that the application users often don't expect or understand. Burst buffers won't fix this. They won't fix this because they're basically caches, and that caching problem stands in the way of it. Okay? So the other part about this is that this is a self-inflicted wound. Other communities have matched their data systems to their needs. The big data file systems have very different models for consistency that provide much better performance for their applications. But why don't we do this? So that's a question for which there's no real answer, because I have no idea why we do this. Why is the question wrong? So to almost all application developers, if you ask them if they need POSIX I/O, they don't know about this very strong semantics. None of them use it. What they think you're asking is, do they need open, maybe seek, read, write, and close? And if they answer no, what they're saying is, I'm going to have to rewrite my code. I'm going to have to restructure all my files. Okay? No one in their right mind would say, no, I don't need POSIX, if that's the way you ask the question. Okay? And we should know that, because a question for which there is only one reasonable answer is not a question. I'll also argue, but this is a hypothesis, so we could all go out and ask our funding agencies to research this, but I would claim that no science application needs POSIX. Many of the applications I know, many of the applications are single reader or single writer. Some of them are disjoint readers and writers, so they don't access overlapping data. Some of them use the file system as a database, and they sort of need POSIX semantics, but in fact, they should be using a database. It would be worth it for them to rewrite their code once, because then life would be so much better. Some applications use it to implement an inter-process mutex. That makes me cringe. There are so many better ways to do that. You could use MPI for that. You could use shmem for that. Some of them use it as a bulletin board, but again, you could use RDMA for that, and they almost always need a very weak form of consistency. I'll point out that correct Fortran codes do not require POSIX in any form because the standard requires unique open. And MPIO is structured with a weak consistency model for the same reasons that Fortran is, to provide good performance. So MPI doesn't need POSIX. Okay. So I've given a number of sort of curmudgeonly stories, things that I see and hope that as a community we can train our students, train ourselves to work past. I really believe that we can solve the problems that we're facing by taking a rigorous and scientific approach. If we don't do that, if we take a sort of qualitative approach, what we think we should be doing without then thinking about how we apply the scientific method to it, I think we've wasted a lot of time pursuing the wrong sorts of solutions. The scientific approach has gotten us just a tremendous advancement. Bill Camp gave some examples, numbers there. I looked at my own career as a graduate student. I was running on a Cray 1 around 100 megaflops. We now see systems at 100 petaflops. This is a billion-fold improvement. This is tremendous. And that has been due to a very quantitative approach to the building of the hardware. And honestly, a quantitative approach to tuning and managing the software that we are using on the systems. We should apply the same approaches to the ways we look at the rest of the software. So I think we can accelerate progress by training our students to challenge the conventional wisdom, but to do it in a way that is scientific. And so with that, I'd like to thank, of course, people who have funded me over the years, my coworkers over my career, my colleagues around the world. This is one of the things I love about this community is we are all colleagues, my students, and especially Ken for his contributions in leaderships and the example that he set as a scholar and gentleman. Thank you.
Okay, thanks, Bill. We have time for at most 1 or 2 questions. And if people are figuring that out, I'm going to ask Bill one question. So, Bill, what if in 1992, all computing nodes are many-core, 100 to 1,000 cores per node? How would MPI have evolved then?
That's a very good question. So we designed MPI even from the beginning to be thread safe. So we were expecting them to be multi-core. Many-core is different, but I think many things would have been there as well. We still need, as Bill Kemp pointed out, you need some way to manage data locality, and you need some model for that. I think we would have built in perhaps some of the shared memory features that we're just now seeing in MPI 3. I think we would have had more time to think about how those integrate with the rest of the model. Things would look different, but I think a lot of them would look the same.
Okay, good. One more question? Yeah, go ahead.
Okay, I have a question related to applying the logic used in the second part of the talk when we discussed the POSIX I, where we blamed the performance on the semantic, because semantic here was like constraints. Can we do the same thing on MPI where we can think of MPI semantic as constraints, and this is why in doing optimization there are some limits?
Yes, yes, and in fact, for example, the one-sided interface in MPI is a good example of that, where there was very precise semantics laid out in MPI 2. It was a good fit for certain needs, but it was in fact a bad fit for many other needs. And MPI 3 made some changes in the semantics while providing a backward compatibility path, and the MPI forum is continuing to discuss other changes, particularly for the one-sided operations, which is one of the reasons I pointed out that MPI is more than just message passing, to make sure that those semantics, as we go forward, match what we can do more efficiently. Of course, that still puts it inside the MPI context. Another talk that I thought about giving, but it's a bit old, as I do give a talk on how to replace MPI, where I try to give some guidance on the things that you need to look at to successfully displace MPI. And there are also opportunities there to use different semantics while preserving the things that have made MPI successful.
Okay. Well, let's thank Bill once again. Thank you.